this going. This thing. Thankfully, today is an easier day for us. We can relax for a second after all of that uh, fun stuff we did. So, chapter 6 now we're on. Is kind of a there's kind of two parts to chapter 6. Yeah, go away. There's kind of two parts of chapter 6 that it's broken up into. We kind of have a review, and then we've got like reaction mechanisms. Good morning, good morning. Um, I remember, yes, yes. Good morning, Alan. Um, Out of curiosity, so I'm using yet again a different computer. The fans are like super loud right now, and I don't have my normal mic plugged in. Is that a problem? Like, do y'all hear me just fine, or is the fan noise like overwhelming? I have no idea. So I have my mic, but I do not have the dongle to attach this to the laptop. Perfect. Awesome. My other laptop decided to have the mic like right next to the fans, and it was like terrible. I don't know why the designers thought it was a good idea. So, the review components of this chapter. Hold on, I think we're a little bit. I'm just gonna move this a little bit. Yeah. Let's put me up front. One sec. Let me. There we go. Okay. Looking at this, the review part is going to be on like enthalpy and entropy and free energy, kinetics. Y'all can have fun with that. We're not going to really focus on these topics right now. We'll talk about when they're relevant. We'll talk about them more. So we'll talk about um, entropy when that matters more to us. We'll talk about kinetics more and thermodynamics when those are applicable. The book has them here now, and I'm going to just move this slightly over. So you're welcome to use those. It'd probably be a good idea to just take a quick read of those, and it would be a good idea to go over that. We're going to do a little bit of the kinetics and thermodynamics when we talk about transition states and all that. Those are important here. But mostly this chapter, we're going to focus on this stuff, arrow pushing. So we're really going to be very good at making sure we follow the rules for drawing our arrows in reactions when we need to, and how to do them correctly. So it's very important that we can clearly see when we're doing a reaction mechanism how the electrons are moving around, because that's all the chemistry, right? It's all about electron movement. So let's just start off a bit talking about thermodynamics quite quickly. So here's our like brief kinetics and thermodynamics review, specifically for the purpose of organic chemistry. So we're not going to focus on all those random gases we did our kinetics on last time. We're going to actually talk about them in terms of OChem. Remember that kinetics means kind of rate of reaction, right? We're looking at how quickly things are proceeding in a reaction. So we're looking at how quickly reactions happen, activation energy, that sort of thing. Thermodynamics, we're looking at kind of free energy of the products compared to the reactants, right? And we saw that both enthalpy and entropy and temperature all had impacts upon thermodynamics. So if you didn't take 113, since apparently that's not a requirement for this course, um, you will want to spend a little bit of time reading that section. You can also, on my YouTube channel, there are the lectures I did on thermodynamics way back last semester. So if you want to look at those to get a bit of information about them, you are more than welcome to. So, but I'm not going to be spending class time here on that. So, cool. Important thing we've seen before is our reaction coordinate diagram. So, here's our typical reaction. This particular one is an exothermic reaction, right? Because we end up with lower energy, with our reactants have higher energy, and our products have lower energy. And we remember we, of course, have activation energy. Fun stuff. Cool. We remember that this little bit here is called a transition state. So the transition state is kind of the physical arrangement of atoms as the reaction is kind of halfway taking place. Although we're going to see it's not really quite halfway. We're going to see it more as looking similar to one side versus another. So for a particular reaction, I might give us, say, this is a reaction we'll learn next chapter. But what happens is we can essentially substitute in, just like we did, single replacement and all that way back when. We can have a similar thing here, a substitution reaction. We're kicking something else out and replacing ourselves in. And we're going to see that that transition state will depend on the energetics of the reaction as it's happening. We're going to see a transition state might look like what's going to happen here is the chlorine is coming in and it's kicking out the bromine, right? So at some point, we might expect the transition state to look something like this, where we have the bromine halfway attached to the carbon and the chlorine halfway attached to the carbon. The chlorine's coming in, the bromine's going out. But at the point where that transition is happening, the transition state, this is what it might look like, right? Where we have kind of partial bonds between the things that are coming in and leaving. And let me just write this out here. This is what we probably would expect, right? Somewhere upon this reaction, as it's happening, we have our chlorine coming in, our bromine coming out. At some point, those will both have partial bonds to carbon in the process, right? Because we're going to see in this reaction, we don't form a carbocation, so we don't actually lose anything and then have something else come in later. It happens all at the same time. And so we might expect this. But depending on the energetics of the reaction, our transition state will actually look closer to one of the two. So it's not usually equally distributed between reactants and products. We're going to see that although I've kind of written, this will be exothermic. So what this reaction might look like, if we look at our transition state here, if we want to look at this and say, well, is this transition state closer to the reactants or closer to the products? Hopefully we can see it's closer to the reactants than it is to the products, right, in terms of energy. So for an exothermic reaction, The transition state is closer in energy to the reactants, right? And again, we see that here. So if we're looking at the transition state's energy, where its position is on the y-axis, it's closer to the reactants than it is the products. And so we have a kind of theory that says, therefore, the transition state resembles the reactants more than the products. Right? Since we have only one reactant in this case, we'll just say reactant. This is, by the way, called the Hammond postulate. Hammond postulate suggests that whatever your transition state is closer to, yeah, sounds good. Sounds good, Alan. Um, the Hammond postulate suggests that whatever your transition state is closer to, that's what it's going to resemble more. And what I mean by resemble is if we look at the reactants, this is our reactant for this. And here's our product. Since the transition state is closer, if we're going to have like a timeline here, the transition state might be closer to the reactant side, where it's going to resemble that more. So as a result, well, we kind of drew it as halfway in between. If we're going to resemble the reactants more, that transition state might more look like something like this, where we can see much more clearly our transition state is much more similar to the reactants. The bromine bond, which is a normal CBr bond in the reactants, has only started breaking down a little bit. And the chloride is coming in from far away. It's not really quite made a bond yet to the carbon. And so this would resemble, this looks more like this than it does the chlorinated form. So the idea here is your transition state, depending on the energetics of your reaction, will resemble either the reactants or the products. And so here, we're looking at, by the way, I need to, if I'm going to be a very good chemist, I need to indicate the transition state with the double, I think they call it a double dagger. I don't see how that is, but whatever. That symbol there means transition state, right? So it looks more like our reactants in this case, because this is an exothermic reaction. If we take a look at the opposite, because why not? What would be an example of an? Well, I don't. I'm making up whether these are exothermic or endothermic, so I'm just making them up as we go. So, but if since an exothermic reaction looked like the reactants, the transition state, for an endothermic, it's the opposite. The transition state resembles product. So, the energy diagram for an endothermic transition looks something like this, right? This is an endothermic. So, whatever that is, that's delta H, right? It's positive, greater than zero. This is our energy, this is our reaction progress. Here's our transition state, right here, and we see the energy of that transition state is closer to that of the products. So I'm going to just use the opposite reaction. I could again be totally wrong if this is the endothermic one, but here we go. Bromine is now going to come in and we're going to now kick out our chlorine. Again, I'm not sure which of these would be the endothermic or exothermic one. We could find that out, right? If we look at the energy of a CCl bond and a CBr bond, we could find out which of these is endothermic and exothermic. But we'll not worry about that right now. Because this is an endothermic process, bromination typically is endothermic. At least free radical bromination is. I don't know about the substitution. But regardless, if we look at that, because this is endothermic, the transition state is closer to the products in energy, and therefore it will look more like it. And so if we're going to look more like the products, we're going to end up actually with the same transition state as before, right? So the transition state resembles the resembles our product here. And so if we draw it, we're going to have the bromine a lot closer, and the chlorine has pretty much left. So it's going to resemble our product. So because this is the reverse reaction, the transition state's the same, right? I mean, reactions typically follow the same path, whichever way they're going, but we see here that the transition state resembles the products in this case. Even though it's the same transition state, exactly the same transition state, in this case, the chlorine's coming in. In this case, though, the chlorine is going out. So we're going to see that our transition state, although it is identical, still resembles whichever way we're going in the reaction. So the if it's endothermic, you'll resemble the products because the products will be more close in energy than the reactants were. If it's exothermic, it's the opposite. So if I ask you to draw a transition state for what's happening, you want to evaluate the energetics. I would probably provide something for you along those lines. And you'll want to make it resemble the correct structure. So I'm making these exaggerated where we see, it's much closer to CH3Br than it is CH3Cl by making that bond extra long, extra weak to showing that it's going away. This is the exothermic. Oh well, I tried. Should we fix that? We can fix it. Ta-da! I have fixed it. Oops. All right, hold up, everyone. I've got to go ahead and fix all this stuff. All because of Jackson. I'm going to remember this come grading time. No. This was... Okay, yes. All right. In the purpose, or in the interest of being as accurate as possible, I will indeed fix all of these. So, I appreciate it, actually. Thank you for looking this up when I didn't want to. Okay. I think that's everything that's fixed. Yes, 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 yes. Okay, cool. So I just switched all my bromines and chlorines, but they have the same idea. So whatever our... No, you're good. You're good. I do appreciate the accuracy element here. So still the point is the same though. For an exothermic process, you're going to resemble the reactants. For an endothermic process, you resemble the products. Again, it's which one is closer in energy. All right, so that's kind of all I wanted to talk about in terms of kinetics and thermodynamics. So, um, again, good idea to refresh yourself. I'm not going to test you on it explicitly yet. If we talk about kinetics, which we will next chapter, um, probably is a good idea if you have it somewhat in your mind. We talk about rate laws. We're not going to really have to worry about calculating anything, but rate laws will be important for when we're talking about substitution reactions and elimination reactions next chapter. So, there we have it. All right. Any questions on the Hammond postulate idea? Just talking about transition states. I do have actually one more thing I do want to talk about. Minor other reaction progress. I do have some terminology. These blue things are transition states. This is an endothermic reaction, by the way, because our products have higher energy than the reactants. This one is an intermediate. And remember that the distinction between a transition state and an intermediate, intermediates can be isolated. Transition states cannot. Transition states are all theoretical. We cannot capture a transition state because it will immediately go to either side. It will either complete the reaction or it's going to go back to the wherever it used to be. So transition states will are not isolatable, but intermediates can be isolated. That means you can capture an intermediate. Interestingly, with the Hammond postulate here, we're still looking in this particular one. We're going to say for this reaction, as the way I've drawn it, in this reaction, it looks like both transition states resemble the intermediate. Because if we take a look at our reactants and products, in both cases, the blue dots are closer to the green dot. Just happens to be the way I've drawn it, right? So we have for both of these, both like the first from the reactant to the intermediate is endothermic, and so it resembles the product. The second one is exothermic, so it resembles the reactant, but for both of those, that is the intermediate, right? So remember, this is a two-step reaction that I've drawn the thing for. So the product of the first step, the reactant of the second step, which are both the intermediate, are what the transition states will resemble. So there we have it. Overall, this reaction is endothermic, by the way, but it consists of an endothermic step and an exothermic step. But it turns out that the endothermic step is a bigger energy loss there. So cool. Alrighty. Any questions on those? We probably will end early today because there's only 4 little bits I want to show. And I did get a request to, on Friday, go over some of the stereochemistry stuff. I do not yet know if I will have time on Friday, but I will let you know. And I'll let you know what time if I'm able to do that. So that will be determined later because I get it. That stuff takes a lot of time and practice. So, but definitely work on that. Do not procrastinate on that assignment because it will take you forever. So, all good for you. Remember, this is the longest homework assignment of the semester, so be aware of that. Okay. let's talk about reaction mechanisms. Alrighty. Oh wait, before we do this, we need to. Yeah, we can talk about these two again. So we briefly talked about these terms earlier on in the semester, but we're going to kind of more generally describe them. A nucleophile just means that it is a site of electron density. Ideally, that means you have a full negative or partial negative somewhere, or just lone pairs. These are generally sites of electron density, and that will make something what we call nucleophilic. Electrophiles are the opposite. And again, electrophile is the easier word to understand. Electrophiles, they like electrons because they don't have them. These are sites of electron deficiency. Deficiency means a lack, right? If you have a budget deficiency, you are spending more than you have. You don't have enough. So with these, we're looking at positive or partial positive charges or empty orbitals. Those are sites of electron deficiency. Sites of electron density would be the opposite, where you have negatives or lone pairs. Empty orbitals would be sites of electron deficiency. So, for example, if we take a look at this thing, we could see that this molecule has some electrophilic. Fluorines are a bad example. Let's use chlorines instead. Fluorines are not going to do this. We're going to see that halogens in OChem generally behave the same way. So chlorine, bromine, iodine typically all behave the same way, but fluorine, being the diva that it is, doesn't do a lot of the things that the other halogens do. So I'm going to just use chlorine this time. We don't really use fluorine in OChem very much because it acts differently than the other halogens. So we see here that this molecule has both. We have here a empty we have an empty p orbital on that boron, which makes it electrophilic. We have an empty orbital there, which means that it can be given electrons. And so we'll see that when we talk about a couple of reactions in 2 chapters from now, specifically hydroboration oxidation, that empty orbital on boron will become very important as an electrophilic site. But if we're just looking here, we also have lone pairs on those halogens, which makes them nucleophilic. B draws electron density from chlorines. You have it the opposite way. Chlorine is more electronegative than boron is, so chlorine will actually draw it towards itself. So normally boron is sp2 hybridized, so it's going to form a trigonal planar. We're going to have the opposite. Uh, we have the dipoles pulling away because chlorine's more electronegative, right? So overall, this is not polar, but we don't necessarily need a polar molecule for it to be electrophilic. And we don't need a full, I mean, those chlorines do have partial negatives, right? And so those are nucleophilic regardless, just because of the existence of lone pairs. We're going to see also, so this is kind of like induction as well, right? We saw electron density being pulled away. Pi bonds, if we decide to be nasty to our molecule and resonate it in a bad way, a naughty resonance, we can see clearly that we have an electrophilic site and a nucleophile, a nucleophilic site here. So alkenes and alkynes, or more accurately, pi systems, pi bonds, are both electrophilic and nucleophilic. And we can see that if we were to resonate them. It would not be good resonance, but we're going to see here that we can have both electrophilic and nucleophilic sites on these. So um, nucleophiles are just kind of any source of electron density. So alkenes will be both electrophiles and nucleophiles, but more often than not, they're going to act as nucleophiles. And we'll see that when we talk more about um, alkene reactions later on. So for right now, we'll just say generally, though, they are more nucleophilic than electrophilic. Just accept it for now. We'll talk about why later on. So we typically have both, but typically we describe alkenes as more nucleophilic than electrophilic, even though we can resonate and get both of those. Just a pi bond means we have extra electrons. So that means more often we're just going to be nucleophilic. And we're going to see in chemistry that one of our reactions, there's really only four things that happen in chemistry, in OChem, believe it or not. One of them is nucleophilic attack onto an electrophile. And so we're going to see that typically alkenes do behave more this way than more as electrophiles. So they can, but typically more nucleophilic. We're going to see that if we substitute them, then things happen more, and we'll worry about that later. So, cool. So, nucleophilic things, I'm just going to kind of make a little table. Just a little summary. We have lone pairs. We have pi bonds. Those are going to be generally our nucleophiles. Again, those are sites of electron density. Electrophiles are going to have empty p orbitals, or they're going to have delta positives or full positives. So remember, lone pairs can be negative charges. We could also get partial negatives through induction, and partial positives also come from induction, right? Just depends what's there. And full positives, which would generally be empty p orbitals. So we have induction working both ways. So if you end up with something that's partially negative, that can be a nucleophile. If you end up with something that's partially positive, that can be an electrophile. Induction works both ways, right? Induction means there's a dipole. Dipole means you have partial positives and partial negatives. So cool, exciting stuff. So let's actually talk about arrows. So our first kind of, dare I say, reaction. This is our first, or let's say the types of reactions. Number one, it certainly would. Nucleophilic attack. And we can use that as our example. Why not? Okay, let's take a look at how this will work. So we know that because the chlorine is more electronegative than carbon, inductively it's withdrawing electron density, which means that this is an electrophilic site. The bromine has all these lone pairs and it's negatively charged, so it's happy to be our nucleophile here. So our first reaction mechanism, nucleophilic attack, is generally written as one arrow. So you have from your nucleophile, you start your arrow from the site of electron density. Typically, that's a lone pair. It could be a double bond. Just like with resonance, we always start arrows from a lone pair or a double bond, a pi bond. And we're going to push those arrows towards our electrophile. So arrow starts at nucleophile. It is either a lone pair or a pi bond. And goes towards the electrophile, which is an atom. So we're going from a lone pair or a pi bond and attacking an atom. So here we have our nucleophile, the bromine, goes and attacks the electrophile, which is our chlorine. And of course, we end up kicking it out. And we'll end up with, here, I'll even draw it. Technically, we'll draw it this way. So we end up having this happen. So we have here what's called a leaving group. We have something that is going to leave as a result of this. So this chlorine ends up leaving because we can't have 5 bonds to carbon, right? Something has to go. So we're going to see that this chlorine is called a leaving group. So our nucleophile will attack an electrophile, and we're going to have a leaving group leave. Makes things, it's a very nice name for it, right? The leaving group will go away. It's going to go be off by itself. We're going to end up with our new molecule. So leaving groups are, I'll give you examples, but I'll just explain what they are. These are typically stable anions or neutral species. either anions or neutral. If they're anions, they're going to be stable. That's going to make them good leaving groups. So good leaving groups, we have generally our halogens. And for this, we're going to see that iodine is better than bromine, which is better than chlorine. Again, we typically forget iodine or fluorine here. Iodine is the most stable because it's the most polarizable, right? We saw that it's the biggest one of those, and it can accommodate that charge more easily. So those are good ones. We have acetates. This would be another example of a good leaving group because it's resonance stabilized. So those make good leaving groups too. We also have, do I want to talk about these now? Why not? This is a very popular leaving group. This leaving group is called toluene sulfonyl, or more commonly tosyl, T-O-S-Y-L. I'll make that clear. This is a great leaving group because of fantastic resonance. So we have lots of different things that can be leaving groups. These are all stabilized anions. So the halogens are stable because they only have a -1 charge. And we saw that iodine's the best one of those because it can take a look at that. We also see that these things come from strong acids, right? Or stronger acids. Like HI, very strong acid. Tosic acid, very strong acid. Acetic acid is not the best acid, but it's much better than something like methane. You know, pKa of 5 is not terrible in organic chemistry. We still consider that fairly strong. So we're still good there. Even better leaving groups, though, if you have some way to make these, water is a great leaving group. Let's see, we have nitrogen gas as a good leaving group. Anything that leaves, we don't typically have hydrogen, but why not? Um, all of these neutral ones are great, especially if they're gases. N2, if you release it, just goes away. So you're going to see some hydrazines, as we'll talk about later, make excellent leaving groups because they'll just thermodynamically shift things towards the products, right? As your nitrogen gas leaves, you are losing a product. The Chatelier's pushes the equilibrium to the right. You end up advancing your reaction more. So these are good leaving groups. Let's see. Bad leaving groups would be things like hydroxide, fluoride, and amide. Absolutely not. These are just kind of destabilized anions. These are unstable anions. And so we don't typically lose those. Or worst of all, we lose a methyl group. No way. It's so unstable. That's not going to happen. Right? So these are bad leaving groups. would be our unstable anions. So good ones are stabilized anions. Better ones are neutral. Neutral things are great. And the worst ones are the unstable anions. And so we're going to see that these three groups here, four groups, would never leave a molecule. They're just not good leaving groups. We're going to see that this actually makes them good nucleophiles as a result. They're more like, I mean, as you see, they're nucleophiles, right? They're just going to come right back and attack something and kick it back out. So we're going to end up not getting a reaction to happen. Um, okay, so those are leaving groups. I guess we should probably talk about what makes nucleophiles good. Good nucleophiles. Good nucleophiles would be, oh, look, it's all of our favorites. These are all great nucleophiles. Typically, this would have to be stabilized with something like lithium or sodium, right? You typically have a counterion with these to stabilize it, because of course you can't have something normal like that. These are all great nucleophiles. We also see that chlorine is back. So chlorine is actually going to be a better nucleophile than the other ones. They're good nucleophiles and they're good leaving groups. They're both. There's not necessarily a correlation between leaving groups and nucleophiles, but your better nucleophiles are the unstable ones because they're going to react more, right? You want your nucleophile to go crazy and attack something. So other things, alkoxy ions, alkoxide, I guess they would be. Yeah, alkoxides. So methoxide. So methanol without a hydrogen, methoxide. Those would be good nucleophiles. Let's see. These are called sulfides. Sulfides, alkoxides. These are all good nucleophiles. Cyanide, good nucleophile. So notice all of these have negative charges, right? They are good nucleophiles. They have concentrated negative charges that are not able to be resonance stabilized. So all of these nucleophiles are unstable anions, no resonance. So those make good nucleophiles. Again, some of these are bad leaving groups, some of these are good leaving groups. We have all sorts of ones. Kind of mediocre nucleophiles would be things like water, ammonia. These are not negatively charged species. These would be mediocre. Let's see, ethanol, alcohols, thiols. These are mediocre nucleophiles, so they're not very strong. Good nucleophiles are strong ones, the ones that are going to react the way we want them to. Mediocre ones, kind of whatever. They can react if we have a very good electrophile. But a good nucleophile can react with a bad electrophile. So that's the idea. There's always kind of that balance. Let's see, what else do we need? That's good enough. Let's talk about electrophiles. We're looking at carbocations, like this, or it happens to be. Those are typically good electrophiles. Um, I mean, I would go so far as to say these are like extremely good electrophiles. Uh, we have ketones or aldehydes, carbonyls because of that induction. Remember, those typically make good electrophiles. Um, and we can even put in alkyl halides here. Though carbocations are going to be even better. Those are going to be the most electrophilic sites because they have incomplete octets. They're very reactive. But carbonyls make good electrophiles. Um, uh, alkyl halides, let's see. Nitriles make good electrophiles, although typically they just do work by induction, but they're not going to leave. So as a result, I'm not going to put them on there. They're not a good leaving group. So I'm gonna actually get rid of that. So um, with the carbocations, you see we have no leaving group necessary because it's got the empty orbital. With the other ones, we have a pi bond, so we can just break, go up, give electrons to the oxygen, or we have something with a leaving group. So um, the tosyl is abbreviated that way. Although for this one, I'm going to go ahead and use an anhydride. This would be a good electrophile because we have partial positive here, and we have a leaving group on it also. So your good electrophiles are things that have leaving groups on them. So that's what makes them nicely electrophilic. Here's another one. If you have a protonated alcohol, that's a very good electrophile because you have a leaving group that's water. You're ready to go. As a result, because of the oxygen's electronegativity, we're going to definitely grab a lot of electron density away from that carbon. So things with leaving groups are good electrophiles. So there's definitely some intertwining things happening here. And so as a result, we typically see these things being there. Okay, so these two first cases do not need leaving groups, but the other ones have leaving groups, so we can have them there. All right, so those will make good electrophiles. Kind of, I don't want to say mediocre electrophiles, but kind of our more boring electrophiles are ones that have pretty mediocre leaving groups. So, or bad ones, just bad electrophiles, I guess we could say. What else do we have here? Things that will end up giving us good nucleophiles if we kick them out. Those would be bad electrophiles. Because even though we still have sites of electron density and deficiency, they're not likely to be attacked because they don't have a leaving group that's very good. They have bad leaving groups. Those leaving groups are actually good nucleophiles, so they're just going to come right back up there. So, because if you take a look at what might happen, if you say, oh, well, here's our nucleophile, let's have it attack this, kicks out our hydroxide. Guess what's going to happen? That hydroxide is going to say, no, 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 I'm coming back. You go away. And as a result, we're going to end up actually forcing this reaction a lot more in that direction. So it's effectively not going to happen. because the hydroxide ion is less stable than the chloride ion is. If we forget that, remember that HCl versus this mysterious substance here, this is a pK of less than 0. This is a pK of 15. We can see that the chloride ion is much more stable. It's still nucleophilic, it can still be a nucleophile, but it's not as good as a nucleophile because it's fairly stable. Chloride is a stable anion. All right, and hydroxide is not. So the hydroxide ion is much more reactive than the chloride ion is, and so we're going to end up actually um, going the opposite direction here. So don't forget your acid-base stuff too. Remember, we talked about how to make things stable. So our best nucleophiles are unstable anions. Our best leaving groups are stable anions. So same thing with the acid-base. So um, sulfur would be a better leaving group than hydroxide would be. They're not great, but they're better. So you can still kind of predict equilibrium that way. So, um, yeah, fun stuff. One more thing to note, just to throw another wrench in here, is that often many nucleophiles are also good bases. Not the case for chlorine, iodine, bromine. Those are terrible bases, right? They're strong acids, so therefore they're terrible bases. But many nucleophiles are good bases. And so sometimes we may have competing acid-base reactions. And we're going to see that next time. That in reality, what will happen here is, yeah, you can kick out your chlorine, or what might happen is you might actually deprotonate and kick out the chlorine later, causing an elimination. We'll see what that is next week. So, fun stuff. We have a lot of options here, a lot of things to keep in mind. So, many nucleophiles are good bases too. And so they can potentially act as bases. So when we're looking at these things, we will consider how to choose nucleophiles that aren't bases or choose bases that aren't nucleophiles, because that'll be an important distinction to make later on. I think I left off one that I wanted to put in there. I wanted to put azide also as a good nucleophile. That might be one that we're not familiar with, but that is also a good nucleophile. Azide, so N3. So azide is N3 minus, has a plus and two minuses, and so we do end up having that. So there's our azide. So that's another one that's a good nucleophile. So again, we have kind of non-stabilized negative charges. That's what makes things good nucleophiles. Alrighty, so that's a lot of information, way more than I meant to. So that kind of ties in with that. This last thing actually tied in two reactions. So the first one was electrophilic attack. Loss of a leaving group is technically the second reaction that we talked about. But I couldn't leave that carbon with 5 bonds there, so I had to do the leaving group earlier. So this is the second type of reaction, is just loss of a leaving group. So we're going to see that for whatever reason, we might just go away, which would lead us with a carbocation and our bromide. Normally, this doesn't happen unless we have certain things helping it. Right? We don't just randomly make carbocations, right? We're going to see the conditions later. We're going to see solvent has a very big impact on this, as well as other reagents nearby. But that's technically the second one. So nucleophilic attack is the first one. Nucleophile attacks electrophile. That can be accompanied by our second mechanism, which is loss of a leaving group. But it doesn't have to. The nucleophilic attack, in this case, also had the loss of a leaving group. Because that just means I chose my example poorly. But actually, I can blame Jackson for that because he said to do it. So, just making fun of you again. That's technically our second one. So, often, often you'll have both happening. You'll have nucleophile attack, electrophile or leaving group leaves. Some part on your electrophile will leave. And so often you'll have those two mechanisms coming together. But not always. Sometimes you'll just have a leaving group leave. Sometimes you'll just have a nucleophilic attack. For example, if we have, say, what's a good nucleophile for us to work with? How about this horrible thing? This technically is two steps. Well, it's one step, but only one reaction arrow is um, our nucleophilic attack here. So we can see that in this case we would end up an O minus. Technically, that's resonance, right? If we just break our carbonyl into a plus and a minus, have our methide attack, we end up now having electrons up there. That electron can go do other things. I'm sorry, that lone pair can go do other things. So this would just be one by itself. That's nucleophilic attack. No leaving group here. This one, right above it, is just losing a leaving group. But that first one we did, way back up here, was two at once. We did one nucleophilic attack and loss of a leaving group. Those are two things happening simultaneously here. So we're going to see that the arrows often do come in many forms like this. If we really wanted to do this second one, we could say it's really only one step by looking at the aldehyde and just doing resonance with it. That's technically that other arrow. And so our nucleophile comes in and attacks it, and we end up with our thing. So that first one was just resonance, technically, and I shouldn't forget my lone pairs. Technically, that first one was resonance, and then we can attack the positive one, but very often we typically will just write it together. We've already seen resonance, so that's not a new thing. That's a little bit more obvious. And so this might be, if you want to look at it, it's really only like one step. So with 3 out of 4 of these reactions, we're going to see that it's just one step. Okay, let's look at the next one. Number 3. Which are just our acid-base reactions. These often come as two things. So if we have, say, acid-base reaction happening, that's a proton transfer. This one typically has two arrows. We have the attack of our base, attacking the acid, grabbing that proton, and then the second one is the bond breaking between the proton and whatever it was on previously. And as a result, we get our sulfur sulfide ion there. So that's the third type of reaction arrow that we'll see. So we've already done these. This was on your first homework assignment where you were doing acid-base, you were doing proton transfer. And if you just take a look at the key on those, you'll see that all of those have two arrows. You have the first arrow attacking the hydrogen, and then the second one giving the electrons from that whatever atom hydrogen bond back to that atom. In this case, it's sulfur. So sulfur hydrogen bond, electrons move onto the sulfur, giving it a lone pair. So remember, we start at a lone pair or bond, and we attack an atom. All right, and then I'm doing more. I'm moving more electrons as we go through. All right, and our fourth one is perhaps the most complicated. And these are carbocation rearrangements. Or typically just rearrangements in general. Though typically those are carbocations. So remember that carbocations are stability-wise, tertiary carbocations are better than secondary or primary. They are so unstable as primary that they will do whatever they can to react, to rearrange themselves so that they are no longer destabilized. So if we have a carbocation here, what's actually going to happen is it will cause one of these hydrogens to move over in what's called a 1,2 hydride shift. We are causing a hydride, an H minus, to move over. We're going to now, I'm going to make that H colorful. It will be a green hydrogen. And now our carbocation has moved to a more stable position. So we have more stable position as a result. We have moved our carbocation over. Not only can hydrogens move around when you have carbocations, but other things can happen too. So here's our neopentane. Let's say it has a carbocation now. What can actually happen, sorry, I'll always use light blue for these. You can actually have a 1,2 methyl shift. And you actually move a CH3 over. So you'll move your carbons around within a molecule to now have your carbocation in a more stable position. So carbocations are happy to destroy molecules to stabilize themselves. So they will move hydrides around. They will move methyls around. They have no problem doing these things. You'll end up destroying your molecule just to make your carbocation happy. And so, as a result, if you have a carbocation that is capable of moving a hydrogen or a methyl group over to make itself more stable, it will do so. And again, we always are looking for going from tertiary to secondary, or sorry, if you're primary, that's the worst. You're going to try and get to either secondary or tertiary. If you're secondary, you're going to try and get to tertiary. Sometimes that's not possible. Like this first example, once the carbocation's on the middle carbon, there's nowhere else that's more stable. So it's going to stop there. In this one, we ended up moving a methyl group over. That carbocation is now tertiary, so we're good. It doesn't want, it's not going to move back anywhere. So um, it will do whatever it can to become tertiary if possible. Another case of something like this happening is something called a ring expansion. What will happen, I'm going to just indicate these. If you have a strained ring, what might happen is you end up expanding your ring. It takes advantage of the fact that some rings are unstable because of the number of carbons there, the ring strain. It takes advantage of that to pop it open. And if we kind of look here, these are those blue and green carbons from before. We have formed a new bond in there. We have now connected the green. I'm sorry, our carbocation would have moved. Hold up. Oh yes, so now our carbocation is going to be on the blue one. Sorry, because the green one. Remember, there's two hydrogens here, so that one's going to still have its two hydrogens, and we'll have moved our carbocation over. Um, and so it's going to be located there now. So the green one still had its two. This blue one, though, only had one. So important to still keep track of our hydrogens. Green one had two hydrogens before. So we're going to end up now moving our carbocation to a secondary position, and it will expand the ring. So you might be saying, well, what the hell? There's this tertiary spot right there. Why don't we just get the hydride shift? You would. You'd get both. You would also get the hydride shift. That's the problem with carbocations, is they have no problem destroying your molecule whatever way they can. You might be like, well, but what's better? And that's a hard question to answer. Both of these would happen. That's the sad part. So it's it's unfortunate that carbocations just destroy things. So they have no problem doing whatever they can to become more stable. And that's the last type of kind of reaction arrow we have. We have nucleophilic attack, loss of a leaving group, acid base stuff, and then these rearrangements. And so these are all done to stabilize themselves, right? So it's the unfortunate case that carbocations being so unstable will happily do all sorts of things to try and make themselves happier. And if multiple options are possible, it probably will do both. So, yeah. So, unfortunately, with this, with ring expansions, by the way, if you have carbocations on primary carbons on these things, these can expand your rings. If you expand them, you will end up adding a carbon to the ring. So notice we started with a 4 carbon ring, and now we have a 5 carbon ring. Interestingly, we could expand multiple carbons. It just gets worse, doesn't it? If we have one here, we can expand it to a 6 membered ring. Why not? Carbocations ruin your molecules. Do it. So this bond here is going to go and attack the carbocation. Not attack. It'll help it to rearrange. And so now we have a 6 membered ring. This green one is now going to be, if we're getting rid of this bond, getting rid of that, and forming this bond, our green carbon is now going to be 2 carbons away from the blue one, and the blue one is where our carbocation will end up. So we will have made our thing a little bit more stable. By expanding the ring, we're getting rid of some ring strain, and we're also making our carbocation from primary to secondary. So we do have some good things happening here. So, yeah, it's fun. It's very fun. Long story short, carbocations go crazy. That is the TLDR here. So, too long didn't read. Your carbocations do all sorts of weird stuff. And we're going to see some reactions produce carbocations, some don't. Carbocations are a lot more common than carbanions are, but carbanions do exist, but those don't rearrange things. They just act as bases, generally, or nucleophiles, and so they'll just very quickly react. But carbocations will do all these sorts of rearrangements. And so it's fun. And so, yeah, sometimes we have all of these happening at once. I'm going to just show you one sequence of reactions, and we're going to see how this works. Don't forget your lone pairs. Lone pairs are very important. Here's our first one. This is, actually, let's do it with a different one. Let's do it with HI or Cl. Why not? HCl. This is, oh, of course I lost them. Are you kidding me? All these carbocation rearrangements. Oh, they hate them. Everyone hates them. So, unfortunately, though, those are oftentimes a favorite in when I ask you to do mechanisms for something. If there's a carbocation that can form, I can make you do so many different things with it. But we'll get there. So, this first reaction here is acid base, right? We have a proton being abstracted off of HCl, which produces Cl minus. We typically will write what we are getting rid of, stuff that's going away, kind of as like just saying we're gonna, it's off to the side somewhere else. We just say like getting rid of the Cl minus. So we'll see that later on in the sequence, but For right now, we're not focusing on it, so we're going to just pretend it's not there. So I put that underneath the arrow with a minus, subtracting that from our reaction right now. Oh, look what we have. A leaving group. Get rid of it. We've lost our leaving group. Our leaving group goes away. I'm putting it again underneath our arrow to indicate that we're losing it. It's going away. I also am putting these as single arrows. These are all equilibrium. Always equilibrium. So, but technically I'm just going to put, we're going forward. If we lose our leaving group, we have a carbocation. That carbocation is secondary. Secondary next to quaternary means we're going to get a methide shift or methyl shift. This is a carbocation rearrangement. If we do that, we will have moved a methyl group over. We now have our carbocation there. It has moved by rearranging itself. And look who's here but our dear friend chlorine. Aha, chloride rather. It came back from the dead and is decided to attack. Thereby giving us our product. So this is just an example of using all four arrows in one reaction mechanism. This is this one is what? A nucleophilic attack. So if we look at what's happened here overall, all we did was add HCl, and we end up with our molecule. And so the mechanism is up here. We're showing how the electrons are moving to get this to happen. So we had first an acid-base reaction happen. We had the hydroxy group attack the hydrogen, thereby liberating chloride. That made it a protonated alcohol. Protonated alcohols are excellent leaving groups because they produce water. Water is very stable. Off water goes. We left with the carbocation, which will then rearrange itself to move the carbocation to a more stable position, a tertiary position. And then our nucleophile, the chloride, which was hanging around there, is going to go ahead and attack. And as a result, we'll end up with our final molecule. So this is a reaction mechanism. Where we're looking at how the electrons are moving over all the steps of this reaction. So a mechanism is all about the arrows. It's all about using correct arrows. And there's four types: acid-base reactions, loss of leaving group, rearrangements, nucleophilic attacks. So there's four different types of arrows we can use. I mean, they're all the same arrow, right? They're all just electrons moving around. But these are patterns that we see. We're going to see every reaction that we will talk about in OChem can be reduced to these four types of things happening. Something that's acid-base, something that's a leaving group going away, sometimes there's rearrangements, those are the least common, and then we have nucleophilic attack, which is probably the most common. So we're going to see here that all of these are very important for us because if we learn these four types of arrows, we can do any mechanism in this class. I can even show you. We'll save this for now. Y'all don't believe me, you never do. What I did in Chem 2 this morning, electrophilic aromatic substitution. Notice what's happening here. This first reaction, guess what? Nucleophilic attack. Second one, loss of a leaving group. Third one, nucleophilic attack. Fourth one, acid base. We have some resonance there as well, but the purple arrows are acid base. We're taking away a proton, and we end up with our reactions. Let's see, I guess all of this was nucleophilic aromatic substitution, or electrophilic aromatic substitution, but same thing here. Nucleophilic attack, base, acid base, and you get your product, etc. So acid base, loss of leaving group, nucleophilic attack, acid base. Done. There's your product. So this is the OChem that you're doing next semester. At this approximately this time of the semester, it's all the same stuff. It's just learning patterns. These are all patterns that happen. And look, we even have carbocations, our favorites. But those are resonance stabilized. So, anyways, all of these happen all the time. And so if we can recognize these patterns of behavior, it'll make it easy for us because we'll always draw our arrows properly. And if we can draw the arrows properly, we're going to see very clearly how a reaction is taking place. And if we do that, we'll be able to predict the correct products. Isn't that fun? Like, how the heck are we going to look at this molecule, this, what is it? 3,3-dimethyl butanol. Put HCl, you somehow get this completely different 2,3-dimethyl, no, chloro comes first. 2-chloro, 2,3-dimethyl butane out of this. Like, what the hell? So, that's the point. Yes. So, practice. Go back to the resonance problems. Those all have correct arrow pushing as well. So, you always want to make sure that your arrows are starting at a site of electron density, a bond or a lone pair, and an arrow always pushes towards an atom, okay, or a bond. But for these four arrows, it's all about moving to atoms. They all go to atoms. When we go to a bond, that's resonance. We are resonating things by moving things to bonds, but in these reactions, we're moving them to atoms. So, cool. Alrighty. So that's actually all of the chapter 6 stuff I wanted to go over. So introducing these four types. We're going to see them throughout the next chapters. So by having them, I will try and identify them as we go through it. And then after that, I'm going to probably taper off a bit because by then you'll be like, oh yeah, nucleophilic attack, no problem. So, yeah. Alrighty. I will let you know about Friday if we're going to do any stereochemistry review. If we do, I would still put your questions in Discord. Just start putting them now. Say, hey, number 4C, or I know some of them is like number 12Q or something, where there's so many. Put those in Discord. I'll see if I have time to do it on Friday. Okay, and I'll let you know. Alrighty. Enjoy the rest of your day, everybody. See you next time. My mouse is off. Okay, here we go. See ya.